Hello, today we're going to start Chapter 8, and Chapter 8 is on exponential and logarithmic functions. We're going to start first with 8.1, which is just exponential growth functions. Exponential growth functions involve the expression b raised to the x power, where our exponent is our variable and b is our base. Now our base b has to be positive and it has to be other than 1. Why can't it be 1? Now the reason why it can't be 1 is 1 raised to any power is just 1. 1 squared is 1. 1 cubed is 1. 1 to the 4th power is 1. So you don't want to have a base of 1 because you're not really going to have any kind of activity going on. For growth functions, your base has to be greater than 1, and that's representing the growth. So we're going to look at our first equation, f of x is equal to 2 to the x power, where our base is 2. We're going to fill out a table just to kind of look to see the shape that an exponential growth has. So this is 2. We're plugging in x to the negative third. We know what negative exponents do, so that gives us 1/8. 2 to the negative second is 1/4. 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8. So we'll do a rough sketch here to kind of see what our growth is going to look like. Our first point is at negative 3/1/8. So I go down or left 3. 1/8 is really close to 0. Negative 2, we're going up just a little more to 1/4. 1/2. 0, 1. 1, 2. 2, 4. And 3, 1, 2, 3, 4, 5, 6, 7, 8. Alright, so we can see in an exponential function, it starts off growing really slowly and then all of a sudden it kind of shoots up. And you should also notice at the end behavior of the graph, you have an asymptote, a horizontal asymptote at y equals 0. So it's going to approach 0 but never actually touch 0 on the y-axis. Okay, so the nice thing about these exponential growth functions is almost the entire chapter is on real-world application. And our first application is exponential growth functions, where it's y equals a times 1 plus r raised to the t power, where a is the initial amount, r, I'm sure you can guess, is the rate of change. But you want to be careful with the rate of change because it's the percent increase. But you want to write it as a decimal. You do not want to write it as a percent. And t, of course, is going to be our time. So there's a pond stocked with 200 fish, and the Department of Wildlife expects the population to increase at a rate of 5% every year. We want to find out how many fish there will be after the first year, 2 years, and 3 years. So we go back to our original equation. We've got y equals, a is representing our initial amount, and in this case we're starting with 200 fish. Then we've got 1 plus our rate. So now here we've got a rate of 5%. If I want to take a percent and I want to change it into a decimal, I take where the decimal point was and I move it 2 spots to the left. 1, 2. So that gives me a decimal of 0.05. So we fill that in as 1 plus 0.05. Remember, we want the rate as a decimal, raised to the t, and in this case our time is 1 year. When you look inside, 1 plus 0.05, those are like terms, so I'm going to simplify that down to 200 times 1.05 raised to the first power. I don't expect you to know how to do this in your head, so in your calculator you plug in 200 times 1.05 and you get that there's going to be 210 fish. Since this is all real-world application, I expect there to be labels on your answers. Alright, so if I'm doing this after 2 years, with the we're assuming the same population increase rate. So I've got y equals 200 times that 1.05, since it's the same rate, but this time I'm going to have it for 2 years. So instead of raising it to the first power, I raise it to the second power. On your calculator, you can just do second enter and change the 1 to a 2, and you get 220.5. We can't have half of a fish, so I'm going to round this. There's going to be about 221 fish. Just round to the nearest number of fish. And of course, for our last one, same initial amount, same rate, so still 1.05, except for our time has changed from 1 year to 2 years. Now it's 3 years. Again, second enter, change the 2 to a 3, and we get 231.525. Can't have a fraction of a fish, so we're going to say that there's about 232 fish in our pond after 3 years if the rate of change is still 5%. Alright, let's look at another example. As seen on TV on Swamp People, the population of alligators increases at an alarming rate, and the population must be controlled. Every month, the population increases by 0.8%. If there are currently 200,000 alligators in the Louisiana swamps, we want to start by writing an exponential growth model, and we want our population to be represented by P after a given number of months. So we're going to take that same growth model, we're just going to give it different variables. So y is now going to be P. The initial amount is 200,000. We're going to have our rate, now 0.8%. We move it twice to the left, 1, 2, becomes 0.008 as a decimal. And we raise that to not t because we want it in terms of m of months. So we combine those like terms in the middle, and we get p is equal to 200,000 times 1.008 raised to the m power. And that's going to be our exponential growth model for this situation. Okay, so next we want to find out how many alligators there's going to be after 6 months. We have two variables. We've got P, we've got M. Clearly 6 months is representing our M value, so we plug it in. 200,000 times 1.008 raised to the M, and M is 6. Again, I don't expect you to know how to do this without a calculator, so you plug it in your calculator. You get 209,794.0603. Just like the fish, we can't have part of an alligator, so we're just going to round that to the nearest whole number and get 209,794 alligators. Alright, part C, how long before there are 250,000 alligators? This time we want to find out our M, how many months, when we have the final number. So our P, our population, is now 250,000 is equal to 200,000 times 1.008 raised to the m power, where we're trying to find out that number of months. The only way we know how to solve this right now is going to be solving by graphing. And we're going to put the left-hand side into y1, and we're going to put the right-hand side into y2. So if you don't have your calculators out yet, press pause, get them out, get your calculator on and ready. When we go to y1, we plug our 200,000 in, 250,000, and then in y2, we put the right-hand side of our equation in. Make sure that you're raising it to the x power. Even though our variable is m, your calculator represents that x on your calculator. Now we have to change our window. This 250,000 is representing a horizontal line at 250,000, so a 10 by 10 grid's not going to work. We go to window. That means we have to go above 250,000, so I went to 260,000. My x's, I just assumed that it was going to be more than 10 months, so I changed it, and I guessed to 40. You're going to kind of have to guess and check on this. See if you find the intersection point. If not, go bigger. So we hit graph. Now our exponential growth model is right here. This is representing the growth of the alligators. The horizontal line is representing when that population meets 250,000. So I want to find that intersection point. So I do second trace, number 5, first curve enter, second curve enter, and then I guess, and I find my intersection point. So we're going to do a sketch of this. Since we solved by graphing, sketching the graph is showing your work. We've got our horizontal line, we've got our growth model, and then we label that intersection point to be 28.004, comma 250,000. And that means that it's going to be about 28 months when the population of alligators goes from 200,000 to 250,000. Alright, so those are all exponential growths of populations. Exponential growth can also be seen with interest at your bank. So our formula here is representing compound interest that you get at a bank. A is going to represent the total amount that you have. P is going to represent what they refer to as the principal. And that's just going to be the initial amount, just like in our other equation. N is the number of times compounded each year. T is going to represent your time, and this is going to be time in years. Banks are always considered in times of years. And R is going to be the interest rate. And just like before, this is going to be as a decimal and not as a percent. Okay, so you deposit $2,000 into an account that pays 6% annual interest. Find the balance after 3 years given different compounds. So if I do it annually, I'm only doing it once a year. If I go quarterly, I go 4 times a year. Quarterly means 4. If I go monthly, my N is, there's 12 months in a year, so that's 12. If I go daily, my N is 365. So that's talking about how many times a month, or sorry, how many times a year it's compounded. So I want to find the amount, A. I invest my principal of $2,000, 1 plus my rate, 6% is 0.06. That's a decimal. And over our N, which is 1, and it's raised to your N, which is 1, times T, and this is going to be after 3 years. So I simplify that down, and I get 0.06 raised to the 3rd power. Again, we're going to do this in our calculator to get $2,382.03. Alright, I want you to press pause, and I want you to find the amounts quarterly, monthly, and daily. Alright, in each of these examples, the only thing that was changing was our N. So here we divided by 4 instead of 1 and multiplied by 4 to get $2,391.24. We changed our 12 to get our new amount. And our last one, we changed to 365. The only reason why I did not rewrite this was because there were so many decimals, I would have lost the value, and I don't want to round, so I used the exact answer when I went in. Alright, our last problem. You want $5,000 3 years from now in an account that pays 3% interest compounded quarterly. How much should you start with initially? So I want $5,000. I don't know how much I'm investing. I've got 3%, which is 0.03 as a decimal. I'm doing that quarterly for 3 years. So that gives me 5,000 is equal to P times 1.0075 raised to the 12th power. I'm going to divide both sides. and you end up with an amount of $4,571.19.